Hello. Hello.
Respected Dr. Ranjan Kumar Behera sir, my dear participants, a very good afternoon to all. This is the fourth session In the first session, we have seen different categories of renewable energy sources. In the second session, we have seen solar energy in detail and integration to PV systems. In the morning, that is in the third session, we have seen wind energy and related topics. Now in this session, we will see advanced power converter control for solar and wind energies. Dr. Ranjan Kumar Behera sir has good teaching experience, research experience, and industrial experience. Now I request Mrs. P.V. Siresha to introduce Dr. Ranjan Kumar Behera. Thank you, sir.
Good afternoon, one and all. We Department of EEE, St. Peter's Engineering College, Hyderabad, welcome Dr. Ranjan Kumar Behera sir, Associate Professor IIT Patna, to 1 week online STTP recent trends in renewable energy sources and their integration to smart grid. Today, sir is going to deliver his research experiences on advanced power converter control for solar and wind energies. Sir received Bachelor of Engineering degree from REC Rourkela, MTech and PhD degree from IIT Kanpur in the year 2003 and 2009. He worked at Hindustan Aeronautical Limited as a trainee engineer. Since May 2009, he is a faculty member in the Department of Electrical Engineering, IIT Patna, where he became head of the department in January 2016. During July 2008 to February 2009, he was a visiting scholar in the Energy Systems Research Center, Tennessee Technological University, USA, and also as a visiting research collaborator at EC Department, University of Pretoria, South Africa during July 2016. He got several national, international awards such as Young Scientist Award in Engineering Sciences from DST Government of India, selected as Featured Engineer of the Globe 2015 USA, and Bhaskara Advanced Solar Energy Award Indo-US Science Technological Forum 2014 for doing solar research in Energy Systems Research Center, Tennessee Technological University, USA. He published 1 or 2 research articles in different national, international journals and conference proceedings. His current research interests include power electronic, high power motor drives, smart grid, IoT applications. He is co-authored a book entitled Power Electronics, Drives and Advanced Applications, CRC Press, April 17, 2020. Sir, good afternoon, sir.
Good afternoon. Thank you so much.
Sir, please start the session, sir.
All right. Thank you so much for introduction. And especially it is my learning stage. I learn and I can. So, good afternoon to everyone. If I can switch off my video, maybe that will be good because it may be little less bandwidth sometime, so it may be ring device. So already last there was one FDP program. So I have already discussed this topic and the power converters, but and the solar and wind. But we work in many areas. So last time I spoke about concurrent design and CSI fed current controller CSI fed PV system. But today we will see some different concept. One concept is that today in the current controller became very much attractive for the grid connected system because the hysteresis current control has many advantages, and that is why the SCC method or hysteresis current control method became very popular, especially if you see in the application of power quality. Also, the hysteresis current control became very popular. In drives also, I used during my PhD. Now also we use as a direct torque control. That is also hysteresis method, but it is not that. That is not the current control, but that is the torque and flux control. So this current control, what is the current control? Current control is nothing, but you want to control a current within a switching band. Band means, for example, I will tell you, you are in your department, you may be, you are professors, and some financial power is given to you. For example, for HOD, the financial power up to 2 lakh rupees is given. And for a faculty up to 1 lakh, that means your limit is that one. That is called the bandwidth. Similarly, in the hysteresis current control also, this limit is given to you. You can control your current within this band. Okay. For example, your reference current, you have 5 ampere current, you can go that 10%, within 10%, you need to control your current. So what we do, in your, when the limit is given, you will operate within that limit. You will not go beyond that limit. And if you go beyond that limit, that will be another point of discussion in the higher authority. Similarly, here this may be destabilize the complete system. Okay, that is why the hysteresis current control, and I can tell you there are many advantages such as fast dynamic, and it can also doesn't depend on the parameters of the network, and there are also many advantages. And along with that, we will see also the LCL filter design as well as the active damping, which is very important today, because if there are resonance or chattering in the network, so how you will integrate to the grid? As soon as you integrate grid, the high frequency component will create electromagnetic interference, and it may produce large amount of distorted waveform in the control circuit. But sometimes you will get a missing pulse. Missing pulse means you will get unsymmetrical pulses in your inverter circuit, where it may destabilize the system. So it is a big study actually. I will not go in detail because it will take long. Hysteresis current itself is will take it is a very big subject actually, because it is a non-linear. It is not a linear controller. Hysteresis method is for example, you have seen a hysteresis BH curve in our induction in the electromagnetic magnetic energy conversion we have seen. And this hysteresis current control method is, if you see that hysteresis is very okay, some noise is coming up. Let me just turn on my mobile. Maybe from mobile I will speak, and from here you can see the PPT. Okay, just a minute. Okay. Now you can hear, sir. Now is it okay?
Okay, sir.
Thank you. Uh, so anyway, let me switch off my video so that the bandwidth will be okay. So this is current control method. It's a nonlinear current. And nonlinear control, most of the controller we design based on linear theory, which is not actually because, for example, you are having a wood. From that wood, you want to make a circle or a sphere. So what you do, you remaining wood, you have to remove it to get a shape. That means lot of material, you want to waste it. So similarly, in a nonlinear control, you want to approximate a linear controller. It is a big challenge. That is why the nonlinear control is used in the hysteresis current control method. And especially, for example, linear control method, you have a transfer function. In the nonlinear control, there is a describing function. So both are different. And that is why this hysteresis current controller is a big theory. And I think I'll go just try to go deep into this one. And then you can see that so many things need to be done in this particular control structure because it is first dynamic and it is very easy to implement. That is why people are interested in this type of the control system. You see, the hysteresis current is used in the drives, integrated power system, a smart grid, even all kind of power electronics controllers. Okay. Then last time, I have not discussed all solar microgrid, which is very important. Like today, we want that whatever we get energy from the solar, we want to directly transform to the grid. So how to do that if your solar, for example, you have a DC-DC converter. Can you or can you step up the voltage from 12 volt to 220 volt? We cannot. By using, even if your DC-DC boost converter, you cannot do that. Because that much voltage development is very tough. It will completely destabilize. And second thing, because of this switching action will be very narrow. Okay, so that will lead to another kind of destabilization in the system. So we will use dual active bridge converter, which is very advanced DC-DC converter, where we will use to integrate different kind of energy sources. Then I will speak about the frequency regulation. Generally, permanent magnet synchronous generator is very good because permanent magnet synchronous generator are very highly rated highly rated machines, okay, generators. For example, above 500 kilowatt, these machines. So this permanent magnet generator, they have one good quality that they have low voltage ride-through capability, and the inertia, what they carry is actually, that is used for the peak load also. And it requires direct drive. So that you know that the permanent magnet synchronous generator required the power converter and the rating of the PMSG, okay, same rating. So this type of system are developed and supplied to any network. There is a problem of frequency. Okay? How to regulate the frequency so that it can develop a, 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 a synchronized frequency with the grid. And then few microgrid design and installation. So you see, today we will see that the methods, design, and active damping, and proportional and hysteresis control method, simulation, and some experimental, we will see. You see, the grid connected system have stochastic behavior. And GCI or grid connected inverter, they need to be first robust and resiliency in the current control taken. And the linear controller are very good, but whereas they are very slow in dynamic. So as and as you have slow dynamic, that means the system may destabilize at any moment when there is a sudden load change. But nonlinear controller have fast dynamic response. So I will tell you very simple story. What is a nonlinear system? For example, you are coming from your hostel to the office, and while coming, suddenly a mobile call came that you have failed in this course. Suddenly, what you are very happy and you are coming, suddenly your mood changes. So just a little input came and completely you forgot what is the happiness at all. And this is called the nonlinear system. Especially the human body is a highly nonlinear. You take any system exists in this universe, starting from the environment to a human being, a reptile, everything is nonlinear. Because we have a limitation in the understanding them, that is why we all, especially, we also try to linearize this and try to understand this. At a high switching frequency, switching converter, there is a large amount of switching loss. And then the nonlinear controller, perturbation towards parametric, if there is a parameter variation, it will not affect on the controller. For example, you see, there was a scientist, his name was Lyapunov. So he developed a theory, Lyapunov theory, in 17th century around. But people, they understood whatever he has written, they understood in 1987, people try to understand what he has written. So what his theory has given, when anything at the minimum energy level, it is sustainable. That is the only thing. That way, it is very nicely designed, and that is called the Lyapunov field theory. And Lyapunov he's a Russian, he gave this theory. After that, there are many theories came, like Korisonov's theorem, and many theorem came for implementation in the nonlinear system. Now, we have a simple single-phase inverter. And this inverter is a grid-connected system. and it consists of LC, L filter, and connecting to the grid. So from the grid, you can take this PLL. So last time, I have already told about PLL. Okay. So PLL is nothing but it maintains the same phase, same frequency of the output wave as input. If your input has frequency F, output would also will give frequency F. If input has some phase difference, output also will have same phase difference. That means both the frequency, it will lock both the frequency and the phase difference, or it is constant. There is no phase difference between input and output. There is no frequency difference between input and output. These are the requirements of PLL. So PLL consists of a phase detector, low pass filter, and VCO, voltage control oscillator. And this gives you the angle theta. Why it is required? This is required to generate or to synchronize with the grid. Okay, that is what the PLLs work. There are thousands of PLLs, so many topologies are available. If you can see the literature, there are available. So we may not go through all the kind of PLL structure. So we will try to go forward for using this our control structure. Now you see here, we got theta. From theta, we got the reference current generation, and actual current you compare. Then you have a proportional plus resonant. What do you mean by, you know that proportional plus integrator control is available. And what do you mean by resonant? Resonant control, sometimes you get a sinusoidal current. Generally, PI control is used when your references or the current reference and voltage references are in DC quantity. But when you have the alternating quantity, okay, so proportional plus resonant converter, resonant controller will help to develop the better performance as well as controllability. With that, if you see here, it is active damping. Active damping means you must take consideration the voltage across this capacitor. So this voltage is taken, and this capacitor voltage is taken as a feedback. Then you find out what is the charging current. Then from here, you can get the reference current and compare with the actual current of the inverter. Error signal is processed to hysteresis band, then pulse generated, and this inverter can work. Now, we want to design the filter. How to design the filter? The most important thing is that this is LCL filter. There are 3 system parameters or storage element like inductor, capacitors. The order of the system is 3. Then there must be minimum voltage drop and damping loss. And another thing is that it should have a less resonance effect. Okay, that is most important. So from here, we can write down the equations, okay, KVL equation you can use here. The equation 1 shows one KVL equation where U is your switching signal. So when the upper two switches, for example, S1, S2 on, it will give plus, and S4, S3 on, it will give minus. So this switching equation, 3 and 4, can be written, and this is the complete equation. From the equation, we can find out the transfer function, and based on the parameter given here, we can understand, we can study this one and find out what is the resonant frequency. Now, the active damping is the most important thing, that we want to control the capacitor voltage also in the filter circuit. And that is how, to minimize the effect of LCL resonance, we need proper damping. And this can be achieved, okay, by using active damping system. So this is written in this mathematical equation. You can see here, this is very simple mathematics only. So anybody can model the system, and then you get the transfer function. Then you get a transfer function Ij with respect to Ig star. Okay. If you see here, this is okay, Ig with respect to Ig star. If you see here, this is the complete transfer function. Now, this hysteresis current controller is control from the output of the proportional plus resistive, the resonance controller. You see GPR is a proportional Kp plus 2Kr omega Cs divided by S square plus omega Cs plus omega. So what is this one? So these are the resonant gain, Kr, and omega C is your cutoff frequency. Okay. Now this Kp, Kr in the closed loop function with the PR controller, you can write down in this way. So from here, when you just manipulate and find out what is the switching function, we have two kind of hysteresis band. You see here, this is our hysteresis band, and I don't know how I can mark. Okay, anyway, this is our hysteresis band, and when this current tracking error, the reference current minus the actual current is E. When the E is greater than HB plus, it will turn off or the turn on the lower switch. If the minus HB, okay, is less than that, then it will turn on this up. That means in the single band, you can see in this line, plus HB line. So what it does, it moves from this plus HB. You can see that both the diagonal opposite positive half cycle is obtained, and when it comes from plus HB to minus HB, so you can see that the negative, okay, that the lower two are on. So this is how you get a bipolar output, plus and minus, plus and minus. Okay, and then we derive this equation. Then another method double band hysteresis control, you see this is the double band. So this double band, you have two bands, okay? Why double band is required? For example, you are going in a road and both sides, the road is moving, both sides of the road, you have a road for the walker, those who are walking, and another side road is for cycling. That means, although you have a one road, main road, you have a side road also. Sometimes they are called the service road also. So that service road also give facility to you to properly drive your vehicle also. So that is what you widens the roads. That means you make double road, okay, like that. So this also double band also. What do? We actually extend this road, and in double band, you have more choice and properly you can control. That is why it is one of the very important thing. But in the double band, what happened? The switching action, you can see here, when we have a positive increasing, when we are increasing positively, you can see that it is plus VDC. When it is coming from plus HB to minus HB, you can see that it is a 0. That means you take with respect to your, you can see here, you take with respect to this place, okay, in the negative rail, you will get 0, okay. So this is how we obtain like this, that you can see one is positive, then 0, then positive 0. So this type of signal is called the unipolar system. Whereas this type of signal in the figure 4a, this type of signal, it is called the bidirectional. So one is unidirectional, another one is bidirectional. So one unidirectional, what is the advantages? There are many advantages. Okay, unidirectional the signal, you will have low switching frequency, where the switching loss will be low. Okay. Now, the complete unit is implemented by using logic gates. Okay, this is the simple logic gate by using JK flip-flop. We designed this logic gate because we need this type of sequence in the PW, unipolar PWM. You get 0, 1, 1, 1, 1, 0. So this logic gate you can design by using this flip-flop circuit. Now this is the output voltage and pulse of S1 and S2. So you can see here, you can get exactly the pulse width modulation type of switching waveform. You see here, at this in the middle at 0.4, if you see, it is exactly following your PWM signal, and it will give you the sinusoidal fundamental, okay, and this switching signal when you take, then we can, you can take the first Fourier transform, you will get the fundamental. Now the same system is implemented with the OPLRT system, and we have OPLRT here, and we implemented this one. And with the system parameters are given here, are 230 volt, 50 hertz, and the DC link voltage is 400 volt. So for this parameters, we actually design, okay, this completely. And now you see here the power, this is our hysteresis band, okay. You can see that the hysteresis band is 0.5 ampere current. And this is your grid reference. Then you can see that in case of single band hysteresis current controller, it operates at very high frequency. You can see this red zone, completely very high frequency. Whereas with the same hysteresis band, in case of double hysteresis band, you can see the below figure, the switching frequency is drastically reduced. And this is the beauty of the single band hysteresis current controller and the modified double band hysteresis current. That means what we do, that by just changing the switching sequences by using this hysteresis band, then you can reduce the switching frequency. So also the efficiency can be improved. So I remember in our long back, I designed a 3-level hysteresis band that further decreases for the multi-level converter I designed. This is not, that was not for the single phase. See here, this is the simulation result of PR-based SCC controller with filter. You see here the dynamic performance, okay? So for step change in the power from 500 watt to 1500 watt, you can see completely here that when the current was very small, as soon as at time t is equal to 0.4 to 5, you increase the power from 500 to 1500. Similarly, the below one, the figure shows the dynamic change in this power with respect to your modified double band. So you can see that in single band, everything is within that, whereas in double band, when it crosses the zero axis, there are lot of switching transits. So how to remove that one? There is another discussion. So here we can see this is our the experimental result of the VG, IG, and I reference everything. And in below one, you can see that there is a change in this current, and this is also shown in the figure 11. Now, in conclusion, being a unipolar PWM technique, modified double band improves the output current waveform, and the switching frequency is very less, we have seen that. And PR controller ensured zero steady state error. To damp out LCL, active damping method is applied. So if you see here, what we have got by using that method, and it is also compared with all the technique which is available in the literature. And you can see that this technique which you use, that has a more efficient than all other techniques. So these are the few references. Okay, you can go through this one. So anyone have any questions till now?
Participants, if you are having any doubt, please ask us now.
If you have a question, you can ask, or you can write in the chat box also, or we will move ahead. Okay. But wherever you have a question, you can ask. Okay. Because why I say this one, but these are advanced topics. So if you have some doubt, again, it may you may forget that one. So I ask in the middle. That's why if you don't have anything, then we go ahead. A 10 kilowatt system here, and when we put the solar system, what must we to take into consideration? First thing is power quality, because if the power quality decreases, then your efficiency, reliability will decrease. So that is why we need to actually give priority to the power quality. So this is a waveform. You can see that your voltage is sinusoidal, but the current is like a triangular. So that is what the solar PV integrated system need many kind of analysis. Okay, first one is the power quality. And then harmonic, they are present everywhere, and it is actually generally it gives rise to the instability in the power system. So there are many harmonic standards. IEEE 929 to 2000 are recommended for PV system. Okay. So what is this PV system say? That the PV system that are connected in parallel with electric utility, they must ensure personal safety, equipment protection, power quality, and utility system operation. So these are the harmonic standard for this for our solar system. So that is why we need to understand this one. First one, the European standard. And total harmonic distortion for the current should be 5% with total current harmonic distortion, and 2% for the voltage harmonic distortion. And within a 1% maximum per individual voltage. So what is that harmonic distortion? You know, we know the harmonic number, okay? 1 is your first harmonic, okay? If it is double, 2, 3, generally first, third, fifth, we generally get. Because you know that power electronics inverter, if you have a square wave output, what are the harmonic? You will have third harmonic, fifth harmonic, all odd harmonic. If the same square wave become a quasi-square wave, then you will see that the third harmonic components are absent. Okay, multiple of 3 are absent. So similarly, so total THD must be equal to 8%, including up to 40th harmonic. If you go on, for example, 40th harmonic means 40 into 50, okay, in India, that order harmony should be within that, all total is must be 8%. So that is why there are different harmonic, and this is the system where we have a solar plant, then MPPT, then we have a DC to AC converter, the local load and protection to the power to the power detection and sending. So this model is designed with the filter design, and in this filter you can see that there is a LCL filter and grid, and the controller is designed by using a state space model. Okay, and this filter was designed, then it is fed. Okay, and this is the design, your plant, okay, transfer function, and you can find out what is it. So this is our system where we install this one, and complete unit is designed and installed here. You can see here the power quality of the current wave. You see here, it is like. So this is the grid under partial loading or shedding condition. So when there is a partial shedding, so what had happened? The source became the sink. And that is why the current distortion increases. And if you see here, there are phase voltage and grid current at full load condition. In full load, you can see that both the current and voltage are in unity power factor. They are in same phase. That means what do you think this one? This is nothing but maximum power transfer. For example, in a power system, you know VI into cos phi is the power transfer. So when cos phi became 1, you have maximum power transfer theorem. So maximum power transfer theorem, we have already studied that the input power or input impedance must be equal to output. So similarly, when your cos phi is 1, V into I into cos phi, that means cos phi is 1, that means you are having the maximum power. So similarly, when this voltage and current, they both are in the same phase, they do not draw any reactive power from the source also. So this is the current and the corresponding THD. You can see that it will be less than 5% total harmonic distortion. So when we have seen in our solar plant, you can see that this one is your red color is your voltage, and the blue color is your current. You can see that all the voltage is sinusoidal, but the current is distorted, okay? And they are also trying to draw current at a unity power factor because of this low partial shedding condition. They are distorted so much. So this is our total harmonic distortion. Now you see, when there is a full load, that is why whenever you are connecting a solar system to your load or to the grid, you must ensure that it is operating at full load. Okay. So this is how you can see both the current and voltage, they are in the same phase. And you can see that the THD also decreased here. Okay. Now, this is also this when the inverter feeds to the grid, actually, you can see that both this voltage and current are in the nearly same phase. Now, when the grid supplies to the DC link, you can see that it is just inverted. Inverted one means what you think this one is nothing but when you draw current from the grid also, you draw it to unity power factor. When you give the current to the grid, that is also at a unity power. And that is what always it maintains the unity power factor. So this is what a 10 kilowatt solar plant was designed and modeled. And the system, most important thing is harmonic studies were carried out for this system. And then we have another project and this one we did it for the this project funded.
మాన్యువల్ గా సెంటెన్స్ ఎంటర్ అయిన తర్వాత లాస్ట్ లో పెట్టండి.
So this one we designed during my stay at USA, all solar microgrid. Okay, the all solar microgrid means, you know, nowadays there are distributed generations. Okay, distributed solar plants, and this distributed solar plant, we want to reconnect it to our actual network. The network may be very complicated. For example, here we have seen these are the complicated network, and you have installed distributed solar plant all over the building, and now you want to interconnect to this network. So when you want to interconnect to this network, so how you will interface? It will be interface with some kind of power converter. So this is network I have shown you. There are CSI fed inverters, current source inverter fed, and then grid is connected, and this is the network. And this complete network, now you will see here, this we will connecting our dual active bridge converter for the PV application. And you see all this network, you have a solar PV, solar PV, solar PV, completely solar energy. Okay. Now you see in the below structure here. Okay, this is our structure. Now you see here dual active bridge converter we utilize, and this dual active bridge converter is connected to storage plant. It is connected to the solar PV. It is connected to DC load, and then we connected with the bus system. Okay, or to the grid. Okay. Now our job is to design this dual active bridge converter for this month's application. Okay. So once it is working fine, you can extend for other action also. So this is a dual active bridge. Okay. What do you mean by dual active bridge? There are input side, side 1, high voltage side, and low voltage side. I have given it because there is a transformer between two bridges, and this transformer is high frequency transformer. Okay, like in case of isolated DC-DC converter, we also use this type of isolated transformer. So isolated transformer, high frequency transformer, what it does, if you see here, these are the high frequency transformer. For example, you take a 50 Hz transformer. 1 kVA 50 Hz transformer will have the size of at least 15 centimeter to 15 centimeter. Whereas 1 kVA high frequency transformer will be less than 5 centimeter to or 4 centimeter to 4 centimeter. This is what the beauty of this converter, that when you are designing this converter, this is very compact, and that you can say that compact power supplies. So there are two bridges. One is LC, this bridge 1 or input bridge, and output. Okay, and these two converters are connected through a coupling transformer or the high frequency transformer, and based on this the turns ratio, you can get the voltage. You can increase or you can decrease. It can be N:1 or 1:N also. Okay, that way you can see that this is a wide application in the solid state transformers, and also it has a lot of application in the power supplies for electric vehicles, charging stations. Everywhere we use this one, and that is why this dual active bridge converter, although it is not reported in many of the literature, many of the books it is not given, but it is a very important converter. And because there is a less number of passive component, and evenly shared current in the switch. You can the current can be different. Soft switching properties. So you can operate this converter at soft switching. What do you mean by hard switching, soft switching? So hard switching, you will see there are turn on loss, turn off loss, conduction loss. Three things comes. Whereas soft switching property, you do not have a turn on loss and turn off loss, because you keep a voltage or current at zero when you are turning on the device. So that means when you are turning on, you are making voltage or current zero. So voltage multiplied by current is equal to zero. That is why the switching loss or the on loss and the off loss, they both are zero. That is why you can do that soft switching technique. That is called the zero voltage switching or zero current switching. Anyone you make zero, your power loss will become zero. And that is the main purpose of this soft switching. And that is what low loss comes into picture. Then high power density is feasible. I have seen that 1 MVA transformer, solid state transformer, okay, it was designed in the University of North Carolina University, State University, and it is designed the 10 MVA transformer by using this dual active bridge. That's why high power density is possible. Okay, so now what is the principle of operation? Like in a transmission system, you have an input voltage and you have an output voltage, okay, or it is sending in the voltage and receiving. And they both are connected through an inductor or through a line inductor. Similarly, here also, the two bridges are connected through an inductor. Inductor is nothing but that high frequency transformer. Okay. So when you are connected, what is the power transfer? Is nothing but V1, V2 divided by X into sine phi. Sine phi is the phase difference between bridge H1 and bridge H2. So that means it is exactly like your power system, power transfer capability. Now, we see here, this is our equation, and because we get here a square wave, okay, output of this inverter is a square wave, and input also nearly it is a square wave, okay. So what you get, the p square is nothing but depend on this one, okay, it is given. Now the switching technique, you see how to switch on. So these are the VSC1, you will get plus V1, 0, 0, and minus V1. VSC2 plus V2, 0, 0, minus V. So this way, you can actually switch both sides, both the high voltage side and the low voltage side. So the average power over the switch, we can find out by taking integration of the power, okay, and that power. Now, for this type of converter, we know that this is this lossless converter. That means input power is equal to output power. So P1 is equal to P2 for a lossless system. Now, DAV operate at constant switching frequency. This is called the phase shift modulation. Okay, there are many switching techniques. One of the switching techniques is phase shift modulation, where DAV operate at constant switching frequency and maximum duty cycle happen at 0.5. So D1 is equal to D2 is equal to half. It solely varies the phase shift phi in order to control the transferred power. Okay. So when we use this switching technique, here you can see that first one and second one is switching for our converter. First one, okay? And S5, S6 or S5 to S8, this both the switching are the second converter. And if the second converter switching is lagged from the first one, power will flow from port 1 to port 2. First one to second one. So if you see here, I will show you. If my switching action lags, okay, this is a low voltage side. Let's take this switching action lags by 5 amount of that. That means power will flow from high voltage side to low voltage side. If the switching action of low voltage side is leading the switching of the S1 or high voltage side, then the reverse power will flow. And this is the beauty of this converter. Okay, you just know that how to just switch this one. So that is what here you can see. When it lags from the input port, then you see that the power flows from 1 to 2. And this is our VSC1. Okay, this is what. And VSC2 is less from VSC1, by like this. Okay. And you can see that these are square wave. Okay, this is the output of an inverter. And we can see that this is a square wave. Then if we see here, then we have a voltage across the inductor or the high frequency transformer is that it is like this voltage you can see. And this is the inductor current, okay. Then we have a power transfer. Last curve is your power. You can see that in the power curve, the lower portion of this one is say where the red color, red portion of this curve. That red portion is that reverse power. So it is the biggest problem in this switching technique. So that means when the power flow from the input to output, there are also some period where reverse power will flow. The red color zone is very dangerous because that is the reverse power flow. So how to reduce the reverse power flow? There are few techniques where people also reduce it to 0, but how to reduce this one is another switching technique we can do. So we have simulated this one. You can see that this is our simulation result. Okay. Now you can see that P in also in each cycle, okay, each half cycle, there are reverse power flow, and which is very dangerous. The reverse power flow, what it does actually, sometimes damage the switches also. So because this reverse power flow also, they will damage the switches and decrease the efficiency of the system. Okay. Now, this reverse power flow can be reduced by using another technique called the extended phase shift technique. Okay. So S1 and S4 do not have the same switching signal, and there are phase difference ratio of D1, and like that. If you see here, this is called the extended phase shift. You can see here both input, this S1, S2, S3, S4, they are differently switched on, but S1, S5 and S6 less from S1. Okay, that is how the power will flow from port 1 to port 2. And then VSC1, you see this one is your square wave output, VSC1. And then VSC2 is exactly like last one, only where changes from the square wave to quasi-square wave, VS1. That means you will see the quasi-square waveform, it is more nearly sinusoidal wave. So VL is shown in this figure here. Then IL is this one. When you multiply this one, you can see that there is a small amount of reverse power. Because of that small amount, it is very highly efficient, highly efficient. Now, this small amount of power, there is a little reverse power flow that you can see here in this simulation result. In the simulation result, you can see that how this reverse power very small became by using this technique. And we compared these two methods, extended phase shift and phase shift method. You can see that in the extended phase shift method, the large amount of power transfer capability, whereas simple this switching method have some limitation. Then we will see the modeling. How to model such converters are very important. Because in the modeling, you need to understand that any system you are going to develop, if the modeling gives you insight into system dynamics. That is why modeling is one of the aspects in our design. Anything you take, you need to model the system. Then you must study the dynamic of the system. Okay, you can model it, find the transfer function, then do dynamic of the system. Then voltage drop across the transistor diode pair is negligible. Transistor switching transients are negligible. Input capacitor C1 is very large, so that it behaves like a constant voltage source. Okay, so that is why we have taken as initially for designing this one. Okay, so how to design this one? First thing is switching. So how to switch the switching? This is the switching function, and the switching function is 1 or -1 for this time period. Okay, given time. Now, this TS is 1 by Fs, and you can know that the VSC1 is V1 into U1. U1 is your switching action. When upper two switches are the diagonal switches are on S1, S2, it will give plus VDC, and when it will S3 and S4, it will give minus VD. That is what 1 and -1 is given. And then VSC1, SC2, you can also define by using switching function U2 into V2. Okay. And then you consider the inductor current and output voltage as a state variable. You can write the simple differential equation for this one, and this is the differential equation. Then this complete system is implemented. You can see here, this is the complete system implemented in Simulink. And then you have this type of system, and we have a double, and then we have a transfer switch. Then this is our averaging model. So I am not going to discuss detail in the mathematics. Mathematics you all can design easily. So these are the few averaging technique by using Fourier series analysis, where you can give a perturbation to a system and find out the averaging of that one. So this is our state space equation. Okay, the A. Okay, you can write down the this A matrix, B matrix, then C matrix, and D matrix. So that way you can note down. So this is the complete dynamic of the system. Now, we need to design the closed loop control. So what we'll do, what can be deviate? First thing is your duty ratio, D. D, you can give some perturbation. And then the voltage, V20, and that also can have some perturbation. And then IL1, that also you can have. L real and imaginary, both you will give. So when by designing this one, what we derive these equations, okay, and based on this, the dynamic, and then this is the parameter, 3 kilowatt system, and the rated DC voltage is 360 volt, and transformer trans ratio I have taken 1:1, okay, because for simplification, okay, you can take 1:n, n1 into n2, so many things you can take. And then transformer leakage inductance, then winding like that. This, then filter capacitor. Always you keep in mind, when we are designing capacitor for the filter, 1 ampere of current is 100 microfarad. According to your current, you must choose, because it is IEEE, any paper that you put more than this value, they will ask why large capacitor is used. So 1 ampere current, you need 100 microfarad capacity. This is the thumb rule in the IEEE. Okay. So this is how we design like that. Then this is the small signal average model of this. Then this is the, by putting all the values here, you get a transfer function exactly like this. So this transfer function you get by using the state space C into Si minus A inverse into B. Now, you need to design the controller. So this transfer function we put here and put in the closed loop system, and you tune this one and find out Kp and Ki. So you can see here, this system is stable. Now, this is the corresponding body plot. You can see that there is no peak and the system has sufficient gain margin and phase margin. Now, this is our stable system. You can see here, our gain margin and phase margin is 60, okay? So like this, the system is stable. Now, you have changed little parameter in the PI parameter here. So you will get another one here, is that the system became unstable. Now this complete unit you have applied for this. You can see there are 4 delays. Z1 by Z are the unit delay circuit. These delays will help to design our switching actions. Okay, so that way we design this one. You can see this is VSC1, VSC2, and this is the inductor voltage, and this is the inductor current, and then we have this power. So if you see here, this one also the simulation result of this complete unit, and these are the also the simulation result for different instance. And now you see here, this is the dynamic actually. The dynamic means, you see here, your power was P2 was 1000, nearly 900, 800 like that. And suddenly you want to increase the power. So you have to increase the current or the voltage. So you see the V2 is 100. And then V2 give reference to 200. So suddenly you can see that voltage is developed 200, and both are tracking very perfectly. You can see that both the voltages are tracking. So the most important thing is that when you are using this one, this is enhancing your power transfer and improving your power transfer. Now, this is our tracking error. You can see that during transient period, there are some error, and this is 0, else in the steady state. Now, you see, I have given two plots, which is given in one of the paper, where they have increased the dynamic voltage from 98 to 100 volt, which is just 2 volt. And whereas you can see that by our controller, we increase it from 100 to 200. So large amount of jump or the large amount of voltage, we can operate. That is what the proper controller, when you design, you have a wide openings or wide range of operation. Whereas if you have some kind of the magnitude, so if your controller is not perfect, so you cannot operate at very high value of magnitude, and variations are not possible there. So then we designed the OR solar microgrid, and each component is designed first. First thing, we have a grid integration with this one, and we have a synchronous link connected to a AC-DC converter, then again DC-DC converter. Okay, that is called the dual bridge converter. So I have, that is why, given 2 boxes. So each box, this one box, first box is your AC to DC converter. AC to DC it can do, and it can also do DC to AC also. Okay, both the direction it can do, because it is a bidirectional converter. And then this DC to DC converter is connected here and fed to this system, okay, to the load. Okay, so AC to DC and DC to DC converter. And this is nothing but your dual bridge active converter. Now we see the result. The black one is our voltage, and the green one is our current. You see, there are different kind of loads are connected. Because of different kind of loads, you can see that there is a fluctuation of the current. Due to this fluctuation, you can see here, the current waveforms are varying. Okay, so but the most important thing is that they always maintain unity power factor. You see here, both the current and voltage are the same phase. So initially during transient period, it may not be same phase, but in steady state you see here, they all are in the same phase. So this is the beauty of this particular converter, that always it operated unit power factor, and that is one of the characteristics of the AC-DC utility friendly converter. Utility friendly means they maintain unit power factor. Now, this is our V1, and you can see that this is our V1. And this is the complete, you can see here, the simulation result. And this is the, when you zoom out, then you can see that what is your VSC1, VSC2, and load voltage, the inductor voltage and current, and the power transfer. See here, the power has both positive and negative cycle. That is how this power transfer to the other side. Then here, this is our P in. So you may ask that there may be some reverse power flow. Yes, there are reverse power flow, but the system in positive, it has a region to action, it can feed back to the source also. Okay, that is what it is. Now you see, we have changed from the reference from 100 to 200. The actual waveform also, it tracked to this original one or reference one. Now this is the current and voltage. So if you multiply, that will give you the power. Now I have shown you in the initial slide that a microgrid, which is solar connected to the isolated load as well as the grid connected system. So this system is given, you can see all are DAV converter. Okay, this DAV converter, then there are synchronous link converters, and then three-phase grid tie inverter also. So this is fed to this DC link. Okay, this middle one is your DC link, DC microgrid, is a DC link, and DC link actually controls all the voltage distribution in the line. Now, this is the simulation result. You can see that the first one is battery voltage, state of the charge, and charging current, and this is Pin. You see here, this simulation result, both current and voltage are out of phase. You see, initially, current and voltage are the same phase, so it maintains unity power factor. And when after one cycle, then you see that there is a reverse, okay, the reverse current flow. So that is also maintaining unity power. Whether it is +1 or it is -1, it always maintains the unity power factor. And similar, this is a P2, and this is the circuit. This one, the first circuit, what we have is that all these upper circuits are the switching circuit, or you can say the gate driver circuit. Okay, and this also gate driver, two gate driver circuit, and then we have two inverters. You can see below there are heat sinks, and heat sinks actually carry the switches. So this is a dual bridge active bridge converter. And you can see there are also, there is a transformer from this computer we control. And the upper one is your base driver or the gate driver circuit. Lower one is your power circuit or switching circuit. This way, this converter is very beautifully operated, and you can see that it is a 10 kVA system, but it is very small, compact in size. And this is the beauty of the high frequency transformer. When you use a high frequency transformer, the size of the converter comes down actually. And nowadays, you can say the gallium nitride, silicon carbide device also come. So this size will reduce to less than 1/4 of this size. So this will reduce the 1/4 of that size actually. So this 1/4 of the size, you can see here, this when you use gallium nitride and silicon carbide, it will reduce to that one. So this way, we can implement very beautifully this dual active bridge converter. At the same time, you can also increase the efficiency of the system. So these are the few experimental results where you can appreciate that how this switching action takes place. And then these are the few, the inductor result. So it is exactly this as per the simulation result. Okay. Now this is your VAC1 and VAC2. Now you see it is very same lagging. You can see here it is less. That means power flows from port 1 to port 2. Actually, this is shown, and this is your tracking error. And after the solar, there are another beautiful aspect, which is a very important aspect. In the permanent magnet based wind turbine system, if it is supplied to an isolation grid, okay, and the isolation integration, you need to have inbuilt frequency. For example, when you are supplying, when you supply the power, sometimes you start the generator. Generator start, so voltage and frequency increases linearly. And suddenly, what happens? This voltage and current increases linearly. When this voltage is changing, and slowly the frequency also developing. Whereas when you have connected to a system, which is 50 Hertz system, that 50 Hertz system, but you are starting the big inertia motor machine, generator, the generator will slowly start building the frequency from 0 to 50 Hertz. So this building time, in case of a grid integrated system, need a lot of attention actually, or it may be damage the complete, or it may be destabilize the complete unit. And that is why this we worked on the permanent magnet based system, and we know that what is the remote area power supply, RAPS, is one of the biggest challenge, especially in India also, it is required. Then we will discuss about the mathematical and the description. Then we will discuss about the direct torque control of permanent magnet. Then simulation and experimental result we will show. Okay. So the RAP system is one of the attractive features, whereas the PMSG connected to a RAP system is really challenging because it is isolated, and nor you have reserve in the power, and that minimal amount of power is connected to maximum connected load. So these create another kind of challenge, how to coordinate both actually. The RAF system is one of that system. And I have seen in the Tirupati, there are few wind turbines, but they are based on double fed induction generators and constructed, I think, by Switzerland. So they are different kind. So PMSG is one of the attractive features of a high energy density and low voltage ride-through capability inbuilt. So RAV system combined with the PMSG and BESS is the best choice. So here we started working on the same principle, that keeping the frequency is kept within the specified limit. Frequency should not be deviated. And second one, power electronics turbines, okay, permanent magnet generator will result significant reduction of power system frequency regulation capability, and we need to operate at maximum power tracking, okay. So the stored kinetic energy in the rotor blade in a large form. So that power system, they are sufficient actually for transient processes. But if you have installed an wind generator in the larger area, when you can say that loads are more than the installed capacity. If your installed capacity is 5 kilowatt, and you connected the load, or loads are available more than 10 kilowatt, then there is a problem. So extra available wind power can be fully preserved, harnessed to enhance the frequency support. Supplementary control needed to be well designed and implemented in power electronics converter. So inertial response, primary frequency regulation, and the reserve capability should be enhanced. So how to do that? By this one. So there are auxiliary frequency controller, okay, inertia control support, drop control, and deloaded control, okay, which is very important, and secondary frequency control, which is we are going to discuss about the secondary frequency control, okay, then for coordinated frequency. Now, gearless structure, the PMSG has no gear, you have a very small gear and the simple way drivetrain, and there is no DC excitation, high power density, even 2 megawatt wind turbines are there. So this way, we can develop this complete unit actually. And then the better grid support during the grid disturbances, the efficiency and reliability. If you see here, this is the complete unit actually. This is our permanent magnet synchronous generator connected to a AC-DC converter, then again to DC-AC converter, and through some kind of filter and interfacing transformer. If you see here, this coordinated frequency control part, it is very important. This controller, we all know how it is working, okay, this controller. But the controller here is the coordinated frequency control. First one is deloaded control, drop control, then how to inertia control. These are the different controls. So if you see here, the DFIG, you have a controller. In the double fed induction generator, you have a pitch angle control and rotor speed controller. And that given as a reference to rotor side converter, which is responsible for the proper coordinating of the reactive power requirement of the double fed induction generator, and as well as the coordinating the required torque and speed performance. And this coordinated frequency control, you can see that there is a normal frequency, then system frequency. And this is the rotor speed control and inertia control, where it can control the rotor side converter, okay, in a double fed. But in the permanent magnet wind turbine, in the storage system, you can see here, this is the F actual, and P is this one, and you can see that this is the frequency range. And then you choose this frequency, and then you have a 0 or the switches, then you can put in the that storage drop, and then inverter control connecting to this. Mode 1, if F is greater than 59.8, and mode 0, when the F is less than 59.8. So this you will get from this paper by Dr. Gao, okay, David Gao. David was Gao, which is, I have also worked many times with him. So, and this topic actually. Then this is the coordinated frequency control that you design, this coordinated frequency. And this is actually properly working. And you can see this wind power, then you know cut in, cut out. And if it is no, then PW is at 0. Okay, then you come to this stage. Like that, you can see that because of the support of the battery, you can have maximum, you can support to the battery act as an inertial support to the system mainly. So this system we developed here in we have a permanent magnet synchronous generator, which is connected through a 2-level PWM converter and charging a DC in the common mode in this DC capacitor is connected through a bidirectional converter to a battery or the dominant road. Okay, sometime we require, and then you connect this one directly from two-level LC filter to irrigation pump. So this is the complete unit we implemented for improving the frequency stability. So this is the wind turbine model, which is you can all of you know, I think. And then this is our direct torque control of our generator side converter. So this converter is controlled here. This is the direct torque control, and we use direct torque control. We take this sensor, the sensor, we connect this actual omega M, and we get from this reference speed. You can get from the voltage, the velocity. You can convert to speed, reference speed, and compare this one. Then a PI controller, you get a reference torque, and then from the voltage and current, you measure, you estimate the torque and flux, and then you feed here. Then through the hysteresis, the control is connected to the two-level PWM converter. So this is what the total network of this one. And then the load side converter, we operated as a VYF control, which is simple control. All of you must be knowing. The pump motors also use VYF control, whereas you have a omega R and omega speed compare, then you have a voltage controller, then it is a switching network. So this is the filter design. So you can see the body plot for the filter, and this is the parameters here. We have, these are the filter parameter, and you can see that DC bus is always maintained constant. And if the DC bus voltage, when there is a step change, it decreases, but it tries to maintain constant. And you can see here, DC bus voltage, whenever there is a load is removed, suddenly the voltage will rise, then damp out in a few cycles. But this is the starter current of the irrigation pump, then the electromagnetic torque, and the speed. You can see that this is your closed loop VYF control. This complete unit is used in the experiment, and you can see that this complete unit, this induction motor acts as a irrigation pump, and this one as a permanent. That is how we can design. So what is the dynamic response? You can see that when you apply a negative torque, okay, here. So now in the negative torque, you can see that when you deloaded the period, your frequency was 50 Hertz, it decreased to this one. Due to the secondary frequency support, you can see from this point, this try to maintain at 50 Hertz. And this is the more beautiful, actually, when you use it, when you will see that it is very good, actually. So this an irrigation load is supplied by PMC, and then DTC control used, and typical result of the laboratory is shown. So we stop here. If you have any question or comment, we can discuss. So if you have any question or comment, I can discuss this one.
Participants, if you are having any questions regarding this session, you can post it now. Yes, once again, I am repeating, the participants who are having any questions, you can post it now. So there are no questions regarding your session, sir. I think it is very brief.
Okay. So if they need any question anytime, they can mail me in this address.
Okay.
They can send me mail. Okay. And okay.
Okay, sir. 1 minute, sir.
Okay.
Okay, sir. There are no questions regarding the session, sir.
Okay.
Yeah, 1 minute, sir. Let me invite Mrs. Divya for the vote of thanks. A very good afternoon to one and all. Honorable Secretary Sir, Principal Madam, Convener, Co-Convener, and our most valued invited guests and faculty members, participants, it's my privilege to propose a vote of thanks for this session. And I, on behalf of St. Peter's Engineering College and entire team, extended a very hearty vote of thanks to today's resource person, Dr. Ranjan Behera. Sir, you explained all the things in a very well-known manner. You explained about the PMHT-based wind power generation for an isolated irrigation system with inbuilt frequency regulation capability. And you explained about the single-phase inverter with the LCL filter in a very clear manner. And also you explained about the hysteresis current controller and about how to eliminate the steady-state error for active damping by using the proportional controller for the grid current error. And also you given the information about the single band and double band hysteresis current control with a relevant example which is linked with a normal road, which is the main road and service road. You given a best example, sir. And also you given the information about the modified double band hysteresis current control logic, and also you shown the simulation results which will be done by you. And also you shown the results and explained it in a very well-known manner. And also you given the information about how to design a 10 kilowatt system. And you given the sinusoidal voltage waveform will be appearing and the current waveform is a triangular wave. So what we can do by changing these waveforms, that one you also explained in a very well-known manner, sir. And also you given the third harmonic component which will be absent by using the square wave. In case of square waves, you are using the quasi-square wave. What will happen there? That one also you explained, sir. And you explained about the 14th harmonic also. And you given the simulation results for this one and the phase voltage and current of the grid at a partial loading and full loading conditions also. And you explained about the single phase dual active bridge converters and its advantages also. And you given a very brief introduction about the phase shift modulation switching technique and where we can use these switching techniques. And also you given the information about the closed loop control of utility friendly AC to DC converters with active dual bridge converters. So you explained everything in a clear manner, which is a very clean session for us, sir. So finally, I am expressing my sincere thanks to Dr. Ranjan Behera for giving the excellent session for us, sir. Thank you very much, sir.
Thank you.
Thank you all.
Thank you. Thank you so much. Namaskar.
Thank you, sir. Thank you. First mic.